Thank you for the nice introduction and welcome to the talk about protecting the control plane, or more or less the kube-apiserver. My name is Kevin Niederwanger. As said, I'm a technical account manager with Red Hat. And as this topic is kind of important, as you will see along the lines, I want to ask you who has already upgraded to Kubernetes 133 or later? Okay. For the others, you might want to upgrade soon. Okay, so this entire talk is based on a real-life scenario, and I will make it as a story, so to say. So I will elaborate on why I did go down this rabbit hole and then basically start from scratch. So if you don't know anything about the kube-apiserver, don't worry, we will get this covered. And also we will check which mechanisms do protect the kube-apiserver as of right now and what remaining issues are in the API server before Kubernetes 133. Okay, so the first question is, why did I go down this rabbit hole? And I did go down this rabbit hole, and you will see all the references at the bottom, so you can read this up on your own, but it is quite exhausting, so I did this for you. And I went down this rabbit hole because of a component in OpenShift, which we call OpenShift logging. This is using Vector by Datadog to collect all the logs from pods and other stuff on each of the nodes, so the Kubernetes nodes, OpenShift nodes. And what we have seen is that the Vector collector, when it has restarted, it sent a lot of requests. That is more specifically list and watch requests. This is a special sort of request which you can do on the API server. And it has fetched those resources, like has fetched pods, nodes, and namespaces with list and watch requests. What we later saw is that we had a very high consumption on the kube-apiserver, and as it turned out, the kube-apiserver does run without resource limits, and this can take down your control plane rather fast. And I have also brought this picture. Don't worry, you might or might not be able to read this. I will elaborate on the important bits. So what we see here at the top is the memory consumption of the control plane node when, let's say, nothing has happened. And it's kind of large with 150 gigabytes of RAM for the control plane node without the activity. And we could correlate the issue with the Vector collector when it has restarted, and you probably cannot read that, but at the bottom here you will see those are list and watch requests on pods, nodes, and namespaces. And shortly after those requests, we have also seen that the RAM usage spiked a bit. That is, over 600 gigabytes of RAM are consumed by the control plane node, which is, kind of bad, as you can imagine. And initially, the nodes didn't have this amount of RAM, and the kube-apiserver kept crashing and crashing. So at this point, it was kind of clear that I don't know what's going on. So I had to basically start from scratch and find out why this has happened. And as it later turned out, when I talked to the kube-apiserver engineering guys, this was not only an issue with Vector, this was a long-running issue in the kube-apiserver, and it has now finally been solved with Kubernetes 133. But more on that later. So, as promised, we will start from scratch. Why is the kube-apiserver important? And what you do see here is like a picture with different components and a user creating a deployment. And in the middle, you see the kube-apiserver, and every time an arrow goes either to or from the kube-apiserver, it is involved in this activity. And at the end of the day, you see that the kube-apiserver interacts with a lot of components without going into the details of the exact workflow here. And the components are the kube controller manager, the kube scheduler, etcd, and then finally the kubelet on the node. So what the kube-apiserver does is it is a component of the control plane, as we see here. That's the control plane, and it acts as a front end of your control plane, and basically it exposes the Kubernetes API. Okay, so far so good. Then the first question is, if you ever put a web server into the internet and it got hammered by something, okay, how do we protect it? And one of the mechanisms which does protect the kube-apiserver is the so-called concurrency limit. So the concurrency limit does limit the amount of requests which it does serve at the same time. And there are different parameters, like you see the default parameters for Kubernetes and OpenShift. And there are two important values here, or two important parameters. That is the max mutating requests in flight. That is the amount of requests which are mutated and are currently being processed. And there is also the max requests in flight. That is basically the non-mutating requests. And you might ask yourself, okay, why are the numbers so different, or the default value is so different? That is, the kube-apiserver is obviously very tied to the etcd, and consequently, if you have a faster etcd, which you can do on bare metal, you can serve more requests. Okay, let us further understand how this protects the kube-apiserver. And for that, we will take a look at the server concurrency limit, that is the amount of requests it can handle. And I will elaborate on why we don't call it requests. So in this example, we will make 2 max mutating requests in flight and 4 max requests in flight. And if we sum those together, we call this the concurrency limit of the kube-apiserver. And as said, we do not talk about requests. The kube-apiserver team uses the terminology of so-called seeds. Why did they introduce seeds and not requests? Because a request is pretty well defined. However, you will have more heavy requests and less heavy requests. And to account for that, we will use the terminology of seeds. That means if you have a very heavy request on your kube-apiserver, you will just consume more seeds than one. So that's why we differentiate here. And now let's make an example. Let's say we have here the guys doing all their work all day long and are fetching data from the kube-apiserver, and they already have 4 concurrent requests ongoing. And then there is the admin, which needs to check if the etcd is alive, and he is unfortunately the 5th request. And the kube-apiserver says, sorry, you are over the limit. I will not answer that important question for you. So, okay, while the concurrency limit in itself is kind of nice, it lacks something like a priority system on top of that to account for different priorities, as said. And the kube-apiserver team has done or has thought the same, so they introduced API priority and fairness. Okay, let's look at that. API priority and fairness is very long in Kubernetes, and it is, I would say, more or less bulletproof, and it basically classifies your incoming requests with the so-called flow schema to any priority level. And how those priority levels are treated in the API server or processed is written down in the new CR of a priority level configuration. So we have basically two new CRs. And I will elaborate on those a bit more because it's very important to understand this concept. So let's look at the default priority level configurations. A side note, I have used here the OC CLI. It's the OpenShift CLI. Please view it roughly as an alias to the kubectl. And if you want, you can ignore all the components which are called OpenShift something. But other than that, the configuration is basically the same in the default Kubernetes setup. So let's take a look. What does all of that mean? So the priority levels have different types like limited and exempt, and they also provide something which they call nominal concurrency shares. And there on the right side, we also see like the queues. And to elaborate on this priority level configuration, it is called catch-all because it is meant to catch all the requests which are not catched by anything else, by any other priority level configuration. That's why it's called catch-all. And as it has not configured any queuing, it will, and it is limited, this means it will reject with HTTP 429, that is too many requests, any request which exceeds these 5 shares. Then there are other priority level configurations like the exempt category. Those are very important for the system health. They run basically without limits and without any queuing, so they are served immediately because they are, so, as said, so important for the system. And then we have basically our queues, where we configure the nominal concurrency shares, and I will not go into the queuing theory. At the end of the day, the queues help you when basically you are overrun with requests to queue them up and then serve them at a later point. But as said, that's a very complex topic, and I will not go into that so much. Okay, so back then we discussed the concurrency limit. So now let's do a bit of math. I know maybe you do not like to do math, but it's kind of important. When we have the concurrency limit, I took here the example of OpenShift. That means the max requests in flight of 3,000 and the max mutating requests in flight of 1,000. If we sum those up, we get 4,000. If we also sum up the nominal concurrency shares and want to know how many seats any of those priority level configurations does have, then we can calculate it based on that. Please note that it is not always an integer value. The kube-apiserver team has agreed to floor those values, and now we have integers. So that means the catch-all category has 7-8 seats. However, those are filled. Okay, so far so good. Now also let's look at the flow schema, because the flow schema, as said, it does the categorization of any request to a priority level configuration, or more or less to a priority level. And that's actually how it works. So if you have a flow schema, it does match to like your request to any priority level. And this is of course based on some code or some rules, and the rule is if you have a matching precedence number, a lower matching precedence number, you are evaluated first. And what we can also see then at the bottom, of course, there is the catch-all flow schema and the catch-all priority level configuration with the highest number because it is meant to catch the rest. And so now we have some set of rules how we can like classify all the requests, and everything should be good, right? Or not? Then let's also take a look at how those flow schema actually play out. So on the right hand side, we see the catch-all flow schema, which then like has some annotation, which is like per default, please don't remove it. And how you distinguish it, we here distinguish by a user. We could also distinguish by a namespace. So we could classify requests by namespaces. Then, of course, we have the matching precedence number. That is the number where it will be evaluated, to which priority level configuration we want to map it, and for which exact resources we want to do that. So, as said, catch-all is meant to catch everything. So you have basically all non-resource URLs and also the resource rules on API and so on, also API groups and so on and so forth. And what the catch-all group does specify as user here is any user which is either not logged in, so system unauthenticated, or the user which is logged in, that is system authenticated. In a very similar fashion, on the left-hand side, you see the exempt category, just with different numbers at the end of the day. But that's it in a nutshell, how a flow schema does look like. Okay, so still the question remains, why did the memory consumption explode? from this, you could assume everything is fine, right? But in fact, it wasn't. So let's go into the remaining issues in the kube-apiserver before Kubernetes 133. And as said, API, priority and fairness, is a priority and fairness system which does calculate your occupied seats based on the requests. Some requests, as said, might occupy more seats than others, and those requests which occupy more seats are so-called list and watch requests. And as the list requests are the harmful thing, I will focus on that. So a list request is basically when you do kubectl get secrets, then you will get all your secrets back, as you know. And this, in fact, is a so-called secret list. So if you do a kubectl get --raw, that's a raw request on the kube-apiserver, then you will see that you will get something back which is called secret list. And that's, at the end of the day, a list of all the secrets. And please note that kind list does exist only on the clients, but not on the kube-apiserver. So if you do the coding stuff, please do not rely on kind list for any sort of thing. That's not advised. And also there is some discussion ongoing about the consumed seats, if this calculation is buggy or not. And what the kube-apiserver now does when you do OC get secrets or OC get pods is it gives you back whatever you have requested, right? And it gives it to you in either JSON, YAML, or protobuf if you are not interacting with the CLI, but that's basically what the kube-apiserver is doing for you. And here actually lies the problem as well. That means when you have secrets and you have, let's say, 400 secrets and you want to give it back because you did the OC get secrets or namespaces, then the kube-apiserver fetches this data into his memory and then later encodes it in one large chunk and then waits until the user has read the entire data. So there is no garbage collector or whatever is in there to protect you from consuming this memory. That's just how it was implemented. That means you are now fetching a lot of data into your kube-apiserver and it is waiting to be read, and the fetching will consume an excessive amount of memory. And for large list responses, that is more specifically, you can exhaust your memory as we have seen. And there is also a paper or a blog post which I have linked, which elaborates on using 400 secrets, each with a size of 1 megabyte. If you just do in your namespace OC get secrets, one time after another, your apiserver will explode. So that's kind of not so good. And this is not only a problem with secrets, so that's important to understand. This can also happen on other resources like config maps, like jobs, like any CRDs, which are very large, or if you just have enough objects, then you can do the same, or you can achieve the same result. And also please note that neither the kube reserved or system reserved protects you in this case, even if you configure it, because the kube-apiserver, as it is so important to your system, runs without resource limits. And this means that as long as there is resource available, he will get it. And on Linux, there is also a process which is called kswapd. And he does not really come to the rescue here, because if you're out of memory, because this memory-hungry process for the kube-apiserver is eating all your memory, then the kswapd does his job and looks for free memory pages. So it uses all his CPU cycles to scan all the memory pages and give the kube-apiserver even the smallest chunk of memory it could find, and does that in a circle. So you're not only out of memory, but you are also out of CPU, and your kube-apiserver might be crashing, which is obviously not a great place to be in. Okay, there, as said, the the mentioned blog post also uses some synthetic tests. And in these synthetic tests, they use so-called informers. This is a client-side library which watches on resource changes. And they figured out if they have one informer which watches on resources, they consume roughly 4 GB of memory. For 2, it's 4.7. For 4, 8, and so on and so forth, it gets worse and worse. And that means just one watcher is able to bring down your entire node. And at 16 informers, the node was gone. Okay, so what shall we do at this point? And the answer is twofold. It depends. As always, if you can, you might want to upgrade, but not everyone can. And I will explain why upgrading solves your problem. So there is the special interest group, API Machinery, which had a proposal for stream encoding for list responses. That is, instead of loading everything from etcd and then encode it in one chunk, to stream those things. And this has been introduced as not alpha, beta, enabled by default because it was so important, feature in Kubernetes 133. Also coming to OpenShift 420. And it will be stable, at least according to the posts, in Kubernetes 134. And they have achieved remarkable changes to the behavior. That means they have tested in the benchmarks with 10 list requests, which had a consumption of roughly 1 GB. And you see those are those lines in different colors are the memory consumption of the control plane nodes. And right here at the bottom is after the change. So that means they have reduced the memory consumption in this particular case from 70 to 80 gigabytes to roughly 3. That is a remarkable gain, and also what we were looking for as a solution to our problem. However, if you cannot upgrade, you are, of course, in a bit of a problem, because the upgrade would solve your issue, but if you cannot upgrade, you need to protect yourself somehow. And one of the approaches, it's not a good approach, but it is an approach, is you can just increase the available memory on your control plane. Of course, this goes only so far, right? Because at some point the memory is, you're probably out of hardware. And there are other things which you can do. So if you are in control of your software and can control how the software fetches data, you can control how you actually fetch any object. So in the kube-apiserver, there is the limit and continue parameter. When you fetch objects, you can then say, okay, I only want to fetch 5 pods at a time, not 500. And go through all the list of the pods. This would be possible, but as said, it requires to change how you fetch the data. Then it's also important to limit your tenants, because as I said, if you have like 400 secrets, each 1 megabyte, and then do an OC get secrets all day long, you bring down the kube-apiserver. This might not happen so fast if you have resource quotas on your secrets. So you can only have 5 secrets or 10. So you do not run into this issue so fast, especially in a multi-tenant environment where one tenant might bring down your cluster. And as said, that's also true for other resources, not only secrets, it can also be config maps, jobs, so on and so forth. And then, why did I elaborate so long about flow schema and priority levels? That's because it is part of the solution. But please mind, it is very dangerous when you impose any flow schema or priority level configuration and you block yourself out of the cluster or block any important component out of the cluster. So it is one possible way to isolate some bad actor. Here you find on the right the example for the logging problem we had, where we created a priority level configuration with a defined amount of shares, which was very low, and didn't allow any borrowing or lending. And if you have exceeded those 5 shares, we reject you with a 429. And for the flow schema, we actually limited it to the API groups, names to all namespaces, and here for verbs list, get, and watch. So that's what you can do on the API server, at least for reading, and only on the pod resources. And then you can also specify some specific service account. And in the very, very similar fashion, you can also isolate any bad actor you identify on your control plane or on your metrics. If you see your kube-api server consuming a lot of memory, you can basically do the same to them as we have done here. And equally important it is to monitor your control plane and API server metrics. As said, the links are all provided. That's upstream documentation. The kube-api server provides a lot of useful metrics to identify such kind of things. And as said, if you have any bad actor, maybe give them a nod that something is off how they do software. And if they do not behave, you probably have no choice in limiting them. Okay, so this does bring me to the closing remarks. Let me check the time. Okay. So the kube-api server is, on the one hand, protected by the concurrency limit. That means you have a set amount of requests which you serve, and if you exceed those requests, something will happen. Not necessarily a reject, but something will happen. On top of that, you have the API, priority and fairness mechanism, which does provide you a priority system for all the requests, so you can classify how you want to treat all your requests. And later down the road, we have the memory exhaustion problem, which can bring down your control plane. And the long-term solution is actually to upgrade to Kubernetes 133 or OpenShift 420. And if you cannot update, then there are all the mechanisms I have elaborated on which you can leverage or cannot in your scenario. So that is most specifically to limit all your tenants in a multi-tenant environment with resource quotas. Please do that. If you have some harmful tenant, you have otherwise no real control. And if you have identified that there is actually a misbehaving tenant in your cluster, then you probably want to isolate them via flow schema and priority levels. And until then, that's probably everything which you can do. So until you upgrade, but hopefully you are interested in upgrading very soon. Okay, that's me. Thank you.
All right, since we're very good in time, we have lots of time for questions. Yes, over there. And gummy bears. Hi, thank you for the speak. I think we are exactly affected by this problem. So we run Tekton on EKS.
Oh, yeah.
We don't have insights in how the kube-api service scaled. And we noticed our engineers use Tekton dashboard, and that one fetches all pipeline runs, task runs in flight. And what we had to do is to have an aggressive cleanup procedure. So at the moment, I think we have history data of a couple of hours, maybe 1-2 days, and our engineers are fed up by this. Does this solve the problem? Can we relax our cleanup processes now?
Basically, so what you encountered without having hard evidence or data, what I think has happened on your cluster is that you have a lot of pipeline runs or Tekton runs, task runs, and if you have lots of objects, they don't necessarily need to be large. They can bloat the API server equally as here. We have also seen from the Red Hat perspective that Tekton is one of the causes of this. I just elaborated on the vector example. because I had more data there. But Tecton can do it equally. And as far as I see your problem right now, I would say yes, this solves your.
Cool. I'll try it out.
Any other questions? Yes, over there.
Possible? Yes. Maybe for us poor souls who cannot upgrade anytime in the future, given that, given the metrics that you're looking at, it's very easy to see, obviously, that the usage is spiking, so that the memory usage is spiking. What would be a good way or a simple solution to try to figure out, okay, what is a natural spike from necessary performance or a spike due to this issue?
Okay. What you want to look at, so the requests which are problematic here are list and watch requests. Watch requests usually are not so problematic than list, because the list fetches the entire data set first, and if you keep getting list requests, you will see that. So I would identify how many list requests a certain user or whoever, a certain namespace or whatever does. And when you see there are certain list requests correlating with your memory spikes, I would then actually use the audit logs and see what do they request. Do they want to request the secrets of all namespaces, all the pods, or whatever it is in there, right? So yeah, that's how I would approach it.
Perfect. Thank you.
Any other questions? 5, 4, 3.5. No questions? Come on. 3, 2, 1, none. Okay. In that case, give a hand for Kevin.